Okay, it's 5:25, so let's get started. All right. So a few announcements. Set 2 is graded, so you should be able to see grades and comments on Gradescope as well as Blackboard. Let me know if there's a difference between the two. Set 3 is due tomorrow, so any questions about Set 3?
We did fully go over for like one meter conversion.
Mm-hmm.
Mm-hmm. Is there a super simple? Like as far as
we actually kind of did.
There was, but it didn't. Like you said here, but then say then write the rest of it. Like it did go over like a one.
Mm-hmm.
I guess.
Mm-hmm. But it's the exact same process. I mean, I can take the entirety of today's lecture to do a simple example.
Let's see. What parts of software? Just for one.
Yeah.
I mean, I'm struggling with all of it, so it's not something we have right now.
Yep.
When do you think the rule that has a terminal and then two variables, terminal?
One variable.
Or yes, yeah.
Yep. So you match any particular character that pushes on a symbol with any other transition that pops the exact same symbol.
Okay, that's
Yep. And so first you have to massage the PDA so every single transition either pushes and doesn't pop, or pops but doesn't push. And therefore you're guaranteed to match correctly. But every push with a matching pop. Other questions about Set 3? Yeah.
So problem number 3, which is about shuffle out.
Mm-hmm.
I'm trying to make up a group. I'm not sure what input we're supposed to use as letters and text. It doesn't say anything about that.
Pick your favorite language over any alphabet.
Alphabet.
Yep. As long as it's some language or over some alphabet, you're good. And if the shuffle of that language happens to be some non-regular language we've already seen, or any non-context-free language we've already seen, just cite it.
Okay.
Like if it happens to be 0 to the end, 1 to the end, 2 to the end, just say we prove that this is not context-free in class.
Okay. Okay.
Mm-hmm. Yep. Other questions about Set 3? So I did get a couple questions about question 1. So for the conversion from PDA to CFG, limit to at most 50 rules for each of the 3 rule types. Yeah. So some people are having trouble with that. So I figured if you're doing 50, you probably already written a program to do it anyway. So I think that's good enough. At most 50, yeah. If you happen to have fewer, like in the case of like state goes to epsilon for the first rule type, if you have fewer than 50 states, then you can't make 50 anyway. So yeah, at most 50. I mean, if you want to include the whole output, you can, but yeah. Any other questions about Set 3? Okay. Set 4 I posted, I think this morning. So any questions about Set 4? Okay. Midterm 2 is on Wednesday. Any questions about midterm 2? It covers, well, it definitely covers up until the end of today. But in terms of material before, I'm not going to explicitly ask about like information that was on midterm 1. Like, I'm not going to ask converted NFA to DFA. Like, I'm not going to ask that. But knowing like NFAs and DFAs are equivalent, that may or may not be important. Like the knowledge of that is important, but not like actually doing the computation or whatever.
So I guess we could extend that, is that we don't necessarily need to know the pumping lemma of regular languages, but
That particular pumping lemma, yes. The context-free one for sure. Yeah, because that was past midterm 1. Any questions about midterm 2 then? Okay, so where did we leave off on Friday?
Decidability and equivalent.
Right, so we talked about this notion of decidability. So we say that a language was decidable if there's a Turing machine that no matter what input it gets, it'll always stop on that input and say accept or reject based off of what the language happens to be. And we also saw that recognizable languages are those where you only had to halt on the strings in the language and say accept, of course. But you're not required to halt on the ones not in the language. Okay, and that'll turn out to be an important distinction. So keeping along those lines, we were able to see various languages about DFAs and NFAs that were decidable. So what languages did we see were decidable? Yeah, a DFA and a NFA were examples. A DFA we saw was decidable because we could say just run the machine on the input, and since the computation must at each transition consume a character of the input, it can't take an infinite amount of time to run a DFA on the input. And so therefore we could decide a NFA. We could decide a NFA instead of just simulating the NFA on the input, because for 2 reasons. The Turing machine is not non-deterministic, so it doesn't know what choice to make. And even if it were, you could, for example, take a loop where you don't read any input at all. It's just a sequence of epsilon transitions, and you never progress further. But we saw that if you convert the input NFA to a DFA, then run the decider for a DFA on the now DFA, now we could decide a NFA because the language of the DFA that's resulting is exactly the same as the NFA that was given to us. So we can decide a NFA. What about a Rex? And this is, oh, closed it too early. It's pairs of R and X, where R is a regex and X is described by that regex. It's in the language of R. Yeah, why is it decidable?
because X is in next line being decided by R.
Well, my task is, I'm given this regex and I'm given this string, and my task is to determine if this regex can make that string. Yeah.
Is it because you could use the idea of ANF, or you could use NFAs to find regexes?
Right, so can I decide a NFA?
Yeah.
Yeah, so is there something about regexes and NFAs that we know? They're equivalent because we can have a conversion between a regex and an NFA. So to decide this, we take on input R and X, convert R into an equivalent NFA, let's call it N, let's say. And then now what should I do?
Run the decider for a NFA?
Right, run the decider. Let's call that particular decider D for a NFA on, well, what 2 things does an NFA, a NFA's decider expect as input? NFA and a string. Well, what NFA do I have? N. And what string do I have? x. So I just feed it the pair n and x. So then, since D is a decider, then it must say accept or reject. So if D accepts, then that must have meant that the NFA accepted the input x, but that also means that the regex would have described that string x anyway. So we should say accept here. And then the other case, if D rejects, that means the NFA did not accept the input x, which means the regex R couldn't have described x anyway. So we say reject. The correctness is pretty straightforward, but is this an actual decider for a regex? Does this run in a finite amount of time on all inputs? Well, clearly step 3 takes a finite amount of time. Does step 2 take a finite amount of time? Yeah, why? Because D is a decider. Does step 1 take a finite amount of time? Yeah, why? Because it's an algorithm that works for any regex. And since the regex is finite in size, the NFA that it produces is finite in size. Okay? Any questions about a rex? I should have called it T-Rex. Any questions, though?
We can't say that step 2 takes a finite amount of time because the string x is finite, right?
No.
We haven't listened to that.
Yeah, the input's always finite, so there's never a problem there. The machine that we had for ANFA was a decider.
Okay.
So no matter what it got, it halted. Yeah. Other questions? Okay. Well, so we actually were able to show that all regular languages are decidable, because the problem of figuring out whether a string is in the language of some DFA, NFA, or regex, we just showed those problems are decidable. So all regular languages are decidable. So I want to take a little detour and talk about other languages that may be of interest. So I want to talk about one, and then we'll use that to solve a problem that we actually may want to solve ourselves. So the problem I want to talk about is called EDFA. So instead of ANFA, it's ADFA, it's EDFA. And instead of a machine and a string, we're given exactly one machine and no string. And what I want to check is that the language of M is empty. Oh, I should say that M is a DFA. This would be very, very different if it's not a DFA. Okay? So instead of being given a machine and a string, I'm only given a machine here, no input at all. Okay? Well, no input string, input machine. So if you have a DFA, you may want to figure out, it doesn't actually do anything. So if I can show that this is decidable, then you can actually figure that out. Well, if you are given a DFA, what is a really easy way for you to check if there's some string that it accepts or not? Well, there could be a final, if there's a final state, that is a candidate for it. But what if I can't reach that final state? What if I can't reach any final states? Would I ever accept a string? No. Well, if I had a state that's reachable, that's final, from the start state, is the language of the machine empty or not? So if you have a DFA and there is a final state that's reachable from the start state, is the machine's language empty or not? No, because there's some path of transitions to get to that final state. And whatever that is, that's the string that it accepts, so it's not empty. Oh, what algorithm is that? To check if there's some state that's reachable from the start state. Pick your favorite graph algorithm. Breadth first search, depth first search, Dijkstra, Ford-Fulkerson, any one of those. Do those run in a finite amount of time? That's the important thing. So, on input M, so now we just got to see if there's a final state that's reachable from the start state. If there is a final state in M that is reachable from M's start state, so I better say accept or reject here. So what should I say? Reject. Because if this is true, then the language of M is not empty, but I'm trying to decide emptiness. So I should say reject here. And then in all other cases, accept. Yeah.
We keep talking about things that, for it to work, if whatever algorithm you use has to run in finite time. What's an example of something that you would say that like this doesn't run in finite time, so we can't use that, or we can't?
We'll see an example hopefully later today.
Oh, okay.
Yeah.
Do we have to say that if the initial state is a final state as well? Do we need to say that?
Well, reachable, good point. You should say in 0 or more transitions. Because if it's reachable, a final state's reachable in 0 transitions, that is the start state. So that would cover that case.
Okay.
Yeah. Yeah, so reachable should mean any sequence of transitions, either empty or not. Yeah. Question over here.
We're pretty sure the DFA is decidable, right?
A DFA is never decidable because a language is decidable. We're given any DFA.
A language in a DFA.
Well, that's actually not important here. I'm given a DFA and I need to check in a finite amount of time whether it accepts any string at all.
No, please, what is ADFA?
Well, ADFA was the language of machine and string pairs where M accepts that string. And so the problem there is just saying, can you check whether or not the machine accepts the input in a finite amount of time?
For any string.
Yeah, for any string, any DFA. Mhm.
That doesn't subsume the case where we have we have a 0 state.
Well, there has to be one state. If it's yeah, so this check at the beginning, right there, that checks if it's a valid input or not, which you can definitely do in a finite amount of time. Okay? Yeah.
It's a good strategy when we're writing, we say on exams or
Yep.
future homeworks, that we look at our steps 1, 2, 3, and break them down like that, say finite.
Oh, you mean it runs in a finite amount of time? Yes.
Finite.
Yes. Yeah. And also justify correctness for sure, but yeah, it has to run in a finite amount of time. Yeah. Other questions? Okay, cool. So, any questions about EDFA?
What is the E one?
Empty.
Empty.
Yeah. So we're going to see maybe 3 more examples of E's of something. Yeah.
What is the A?
Accept
Accept.
or acceptance. Yeah. It's just a name, but that's what it represents to us. Okay. Okay. So one thing that is quite troubling about, say, PSET 1 was that we asked you to present a DFA for a particular problem. And the poor grader has to figure out if the given DFA that's from your submission matches the the sample solution that we provide the grader. And one may want to know, are these two DFAs actually the same? Even if they look completely different, are they actually the same? And the problem there is figuring out whether they actually have the same language. So the problem I want to talk about next is EQ DFA, which means equivalence or equivalent DFAs. So instead of being given either a machine string pair or just a single machine, here we're given two DFAs. So I'm going to be given M1 and M2. So M1 and M2 are DFAs, and they have the same language. And certainly, if we can show that this is decidable, then we can actually write a computer program to figure that out for us. Figure out whether the two machines have the same language or not. So, how do you think we can do this? Any ideas? So here's a good idea. If you're tasked to prove that two things are equal, in this case sets, languages, how can you do that? Sorry? Exactly. If I can show that L of M1 is a subset of L of M2 and the other way around, are they equal? Okay, let's see. So I'm not going to actually write a whole algorithm like this, but it's easily constructible from this. So this is the same as determining if L of M1 is a subset of M2's language, and L of M2 is a subset of M1's language. If we can do that, that's fantastic. What's another way to write subset? So a picture will help. So let's just say that we're in this first case. So M1's language and M2's language may or may not be contained within one another. So let's say M1's here, and let's say that there's some intersection and M2's out here. There may or may not be, I don't know. So in this particular example, M1's language is definitely not a subset of M2's language. So how do you know that it's not a subset? That's actually exactly what it is. But let's get a more intuitive idea. In this particular Venn diagram, what do we want to be not there at all? Yeah, the stuff right here. We don't want this part to be present at all. In other words, I want this part to be empty, right? How do I represent that shaded area in terms of L of M1 and L of M2?
The complement of the intersection of the two?
Well, let's see.
Minus complement of the intersection.
Yeah, so I want to talk about the actual area. So it's definitely in L of M1, but it's also not in L of M2.
L and M1 minus.
Yeah,
the intersection.
yeah. So it's equal to L of M1 minus the complement of M2. But another way of writing that is L of M1 intersect, not complement on the first one. L of M2 complement there. So I want everything, so that shaded area right there represents everything that's in M1, take away the things in M2's language. But another way of writing that is the thing I wrote below, which is the things in M1's language and not in M2's language, which is just intersection. Conversely, for the second subset, what area do we want to be also empty? The part that belongs to M2 over here. I'm not the best at drawing or shading. Anything arts and craft related. All right, so this is just L of M2 without M1, which is just L of M2 intersect M1 complement. Yeah.
That looks like symmetric.
Yes. Great point. It is symmetric difference. Because these are the strings that belong to exactly one or the other. All right. Well, if they're equal, what do I know about both of these regions? The shaded regions.
They don't exist.
They don't exist. So they're both empty. All right. Well, if L of M1 equals L of M2, then this implies L of M1 intersects L of M2 complement, so the first guy, union with the second one, is empty. So if either one of these two is non-empty, then this union is not empty. But if they're both empty, then the union is empty. Okay? So this is just a way of saying if they're equal, then the first part must be empty and the second part must also be empty. Yeah.
Can you say just the complement of the intersection is 0?
But I want the stuff that's, I don't want the stuff out here.
Well, yeah, but isn't that stuff the complement of the intersection?
It includes it. It includes the stuff that's in L of M1 and L of M2, but also the stuff outside too. And I don't want any of that.
Well, yeah, but if the intersection, what if they were?
Well, what I could do is the complement of the intersection, then take away the complement of the union. That's another way of doing it. But via De Morgan's laws, it's exactly the same as this.
Okay. Maybe I'm just thinking of them being exactly the same.
Yeah. So if so just both parts of the union just say that I want both of these two regions to be empty. Okay? Well, can I build a DFA for this whole thing? Yeah, why?
Closed under intersection.
Closed under union, intersection, and complement. Okay, well I can build a DFA for that part. Could I check whether that resulting DFA's language is empty? Yeah, why? We just proved that EDFA is decidable. And so therefore, I can do this check. I didn't say that it was the fastest algorithm. I didn't say it was efficient or pretty. I'm just saying that you can do it. Yeah. No. No. I should have wrote a program, but no, they don't. Yeah. They, in theory, could. Any questions about EQ DFA? Is EQ NFA decidable? Yeah. How? Just convert to a DFA, run that algorithm. So we can get equivalents of regular expressions, regular grammars. Anything with the regular languages seems to be decidable. Or testing for emptiness. Any of that's decidable. I want to do another one, and then I'll actually talk about a very interesting question right after that. So I call it all DFA. So we're back to a single machine. M is a DFA, and it accepts everything. Every string. So there are actually two approaches we can take for this one. So how can I check if a DFA's language is every single string? Any ideas? Well, there are infinitely many strings. What was that? Yeah, so basically like that. Every state that I could reach from the start state is a final state. So that's one way. Including the start, yeah, just like before. What's another thing, another way we can approach this? If the DFA that's given to me really does accept everything, what is the complement of that language? Empty. What if it wasn't everything when it was given to me, what is the complement? It's not empty. Do we have a way of checking for emptiness?
Yeah.
Yeah. So the first idea is run similar algorithm for EDFA, but invert final, non-final states. Because it's a DFA here, that's the only way. That's the only reason it works. But the other idea was to, I did it backwards. Idea 2 was to check no. I wrote both of them in one statement. All right, so the idea 1 is check if the complement, if every, I'm falling apart here, if every reachable state from the start state is final, and then the other one is invert final and non-final states. And check for emptiness. That's what I meant to write. So either just check if every single state you could reach is final, or just swap final and non-final for complement as we've seen before, and run the decider for EDFA on the resulting DFA. Either method, they're actually exactly the same method, but they seem to be different approaches. Okay? The decider for EDFA. Yeah, so check for emptiness means just run the decider for EDFA. Okay? Any questions about all DFA? So you may think, well, okay, everything is decidable for DFAs, it seems like. It seems like all this theory about DFAs was solved a long time ago, and we're just building up to eventually we show a language is not decidable, but everything about DFAs seems to be decidable, right? Actually, there's actually one language that I know of that people still don't know whether it is decidable or not about DFAs, believe it or not. And it's this guy. So, I mean, I could put this on a homework, but it's an open research problem, so I won't. I'll be nice to you. So, I want all DFAs M. So I'll note that this is open. M is a DFA with alphabet 0, 1. So we're starting off nice. And accepts at least one string representing a prime number. So I'll put this out as a bounty. If you can figure out whether this language is decidable or not, you instantly get an A+ in the class. I'm not kidding about that. But I actually don't know what a good method to do this is. Can you show that this is recognizable? So here's an idea. Just enumerate the prime numbers in binary, and then just check for each one whether the input DFA accepts it or not. If it ever does accept a prime number representation, then I say accept. But can you show that if you do this strategy, you will never accept a prime number? And I don't know the answer to that. So open problem, A+ if you solve it. So it turns out even today, there are still open research problems about DFAs. And it's going to get much worse once we go into the context-free languages. Any questions before we move on? Okay, so when we first talked about decidable languages for DFAs, we talked about a DFA and a NFA, all that stuff. Then we talked about the emptiness question for DFAs, NFAs, whatever. Then we did equivalence, and then we did does it accept everything or not. So let's start off easy for the context-free languages. So let's talk about a CFG. So instead of a machine and an input, it's a grammar and an input. So G is a CFG, and W is generated by G. Should draw my G's better. Okay. So you may think, well, a DFA was totally useless, right? This is actually really important, this language a CFG, because if you want to implement your compiler as a context-free grammar, that's just saying your program compiles or not. Okay? So if it's in the language of your particular compiler, then this problem will help you solve that. Okay? So how could we show that a CFG is decidable? Well, it seems kind of hard, right? Because CFGs are inherently non-deterministic. I don't know which rule to apply. And I don't know if after a while I may or may not end up with the string I want, right? Is there some easier representation of CFGs that we saw? Chomsky normal form. If we have a grammar in Chomsky normal form and an input of length n, do we know how many rules to apply? Yeah, how many was it? We actually showed a derivation in class. It was 2n minus 1. Is 2n minus 1, once we get the string, finite? Is every derivation of length 2n minus 1 finite? A finite number? Yeah, it is huge. I didn't say this was fast. But is it a finite number? Oh, okay. So let's try that. So we're given as input G and W. So I can't say this for any CFG, but if it's in CNF, now I can say something. So convert G into an equivalent CFG in, I'm going to call it G prime. in CNF. Does that algorithm take a finite amount of time? The conversion process. Yeah, we were able to show that each of the steps can be done in a finite amount of time. So if it didn't take a finite amount of time, I better not progress beyond step 1 here, because then I can't guarantee anything. So there's a little bit of a special case we have to handle here. Do you know what that special case is? The empty string. What is the length of the empty string? 0. What is 2 times 0 minus 1? Negative 1. Could I generate all rule applications of length negative 1? No, we can't. I consulted with myself. All right, so we gotta check for the empty string because that's a special case. Is there an easy way I can check whether a grammar in CNF can make the empty string? Yeah, if the start variable makes it, then we're good. But we gotta check if W, the input string, is actually the empty string, because there's no reason to do the check otherwise. So if W is empty and S, the start variable, makes the empty string is a rule, then accept. So certainly I can make the empty string this way. What if S to make the empty string is not a rule? I should reject. Because if the W is the empty string and there's no rule from the start variable to make the empty string, there's no other way to do that, as we have seen. So if W is empty and S to empty is not a rule, we should reject. Okay. Yeah.
Doesn't any grammar in CNF have that first one that goes to the empty string? Or
No.
not all?
Only if the original grammar did. Only if the original grammar could make the empty string.
Okay.
Yeah, because then we propagate the empty string rule up to the top. But if it doesn't make the empty string, we didn't change the language at any point, so it wouldn't have it in the CNF grammar. Okay, so we handled that special case. Now, what was our idea? To figure out if W can be generated. Yeah, so just check all 2n minus 1 rule applications. Applications of rules of length 2n minus 1. So let n be the length of W. I should generate all derivations of length 2n minus 1 if any of these results in W, accept, otherwise reject. Okay, so a lot of these, since we don't care about how long this actually takes, we will probably next week. Since it doesn't matter how long it takes, I might as well just try every possibility. There are much faster algorithms. I think chapter 2 mentions one of them, but we're not concerned about that here. Just try every derivation of length 2n minus 1. And if any of them give W, then we're good. Otherwise, we reject. Okay? A lot of these are just brute force simulation. is a PDA decidable? Yeah. Can we convert a PDA to a CFG? Yeah. Does that algorithm take a finite amount of time? It may take a long time. I don't care. It may take till the heat death of the universe. I don't care. So a PDA is decidable as well. If we instead happen to solve a PDA and show it's decidable, then a CFG is decidable because we can convert a CFG to a PDA. Okay? Any questions about a CFG or a PDA? So when we did the regular languages before, we talked about the acceptance for each of the models. Then we talked about emptiness. So let's talk about emptiness here. So ECFG. So if I happen to solve ECFG, then therefore I also solve ePDA by the same reasoning. So very similar to before, G is a CFG, and it generates absolutely no strings whatsoever. So this seems a little bit tricky because I may have something like this. Right? I may have something like that as a grammar, right? Where the start variable is s, and since the only rules that I can apply are s goes to a goes to s, and then I can't ever generate anything full of terminals, but there's still a rule that has terminals on the right-hand side. So you could say, well, delete that. But in another grammar, I may or may not be able to. For instance, if I have, in addition to this, I have something like that. I can never get a string that's entirely full of terminals. I can get a string of terminals with variables in it, just by applying s goes to ASA however many times I like, but I can't get anything full of terminals. So what could I do instead? You could, and that is a strategy. But let's try to think of something other than Chomsky normal form. So I'll just give an idea of the Chomsky normal form. Convert it to Chomsky normal form, then make a directed graph on the no, that actually won't work because it has two variables on the right-hand side. I was thinking that you would have a directed graph start with the vertex S, and you see if there's any path from the start variable to any of the other variables that happen to make a string only full of terminals. But because there are two variables, you can't actually work with that very easily. Yeah, you can't work that easily. So what could I do instead? Well, it seems rather enticing. I want to delete that rule, right? But that rule may or may not be useful, right? It may happen that the variable on the left-hand side, if I change this, let's say, no, I can't change it. But it may or may not be useful for the variable on the left-hand side in some other rule. But maybe what we can do is a bottom-up strategy. We can start with the variables that make terminals. So in this case, I know that B, the B variable, can make a string full of terminals. And then I look up and see if I have a rule where all of the variables on the right-hand side can make a string full of terminals. What about do I know about the variable on the left-hand side? It can make a string full of terminals. Then I just keep going until I check whether the start variable was ever said to make a string full of terminals or not. So that's the idea here. So mark all variables that explicitly make a string entirely composed of terminals. So, like in this grammar's case, I would mark B right at this step because it makes a string entirely full of terminals. And then, for every rule, if all variables on the right-hand side are marked, then mark the variable on the left-hand side. And if at any stage I look through every single rule and I don't mark a new variable, then there's no point in me doing this process again. And so therefore I'm done. So continue until no new variables are marked. Then check if start variable is marked. Okay, so I just check if the start variable is marked, then there's some other variables for which it was marked, for which they were marked, and then therefore there were some other variables maybe that generated a string full of terminals. Okay? So like in this case, I would mark B, but since B does not appear on the right-hand side of any other rule, then no other variable is marked. And so therefore, since the start variable S was not marked, therefore I can conclude that this grammar's language is empty. Because there's no way to get to the parts where it actually makes the terminals. And makes only terminals. Yeah.
So if the start is marked, we reject, and if the start is not
Yes.
marked, we accept.
So, yeah, so if start is marked, in this case, we reject. Why do we reject here? Because we just determined that the start variable can make something full of terminals. And then otherwise, we accept. So I'm not giving the on input whatever, but this is just exactly what you would put in a description like that. Okay? Yeah, we should check. Great question. So could I mark all variables so the first part, where they explicitly make terminals in a finite amount of time? Yeah, there's only a finite number of rules, and I can just check on each one. Easy. What about this recursive thing, where I keep doing the same process over and over and over? Could that run for an infinite amount of time? No, why? Yeah, if I mark a new variable, then I keep going. But there are only finitely many variables, so this loop can only progress a finite number of times. Okay, and so this keep going until new variables are marked loop, that can only happen a finite amount of time. So therefore that we're good there. Check if the start variable is marked. Again, finite amount of time. And then rejecting and accepting that's finite as well. Any other question? Yeah.
You don't need to have a case if it generates only terminals, non-terminals,
Well, I say that here. If all variables on the right-hand side. Yeah. And if it happens that one of them, I've not yet determined that it can make terminals at all, then I can't mark the one on the left-hand side
okay.
necessarily. But I'm going to go through multiple times and keep going until I can't mark a new variable. Any questions about this? Yeah.
I don't know. Sorry, I was looking at one question, but like, if there's a rule that goes to, or the state that goes to a rule that's like, or a variable goes to a rule that's all terminals, also like terminals and variables.
Yeah. So like if it was like this?
Like more than one. Oh, it's chunks more than one.
No.
It's not.
Not necessarily. It doesn't matter here. So you mean multiple variables like that?
Like a bar, like more than one.
That just means multiple rules.
Right. But like if there's a mixture, like one's like all terminals and the other rule that goes to is like has variables.
It doesn't matter. I look through every single rule and I mark that single variable in everywhere. I mark the variable, not the rule.
Right.
Because I can choose which rule to apply. Yeah, I don't have to pick that particular rule. I could pick any rule with that variable on the left side. Okay?
So like if A is marked right now, the lowercase a, then B is marked, right? And then,
I don't mark terminals. I mark variables.
okay.
Yeah.
And
Yeah.
right now, we would no longer mark B because it's
Yeah.
not all terminals.
Yeah, I would no longer mark B. I actually wouldn't mark anything because there's no rule with only terminals on the right side. Other questions? Yeah.
Currently, we don't know mark to start state, so we don't.
Yeah, no, here, like in this example grammar, I can't mark anything. And so therefore, since it's not marked, it can't generate any string of terminals. So what is the language of the grammar? It must be empty because it can't generate any string of terminals.
So if you reject, it means.
No, so I say here, if the start variable is marked, then we reject, meaning that the grammar has something in its language because we're trying to decide emptiness. And then otherwise we accept. Other questions?
What if we have B goes to A, all B goes to P, A.
So something like this?
Right.
Yeah.
So we still have B.
Yeah. Yeah, because there is a rule with B on the left side that can make the only terminals. There is a rule. So I would mark B in all places. I'm marking the variable, not the rule, because I can choose the rule.
And if A goes to S or B, we mark A as well.
Yeah, so if I happen to have this, then I know B is marked, so therefore I mark A. And then now I look at all the rules where all the variables on the right side are marked. Well, there's one S goes to A. A is the only thing on the right side and it's marked, so I mark S.
Wait. Why did you mark A in the first place? You said you should only mark it if all variables are marked.
Correct.
S wasn't marked. B can go to A.
Yeah, vertical bar means multiple rules. Those are two different rules.
Okay, so just looking
It's not the same right side. Yeah.
has all variables not one rule.
Yeah. Mhm.
Okay.
Yeah, in that one rule. Other questions? So I just want to leave you with one additional question. Could we decide EQ-CFG? Or all sub CFG?
if you do the CNF of the CFG and you did a CNF of another CFG,
But if we did the same strategy that we did before, context-free languages are not closed into complement or intersection. So that necessarily won't work. And in fact, both of these languages are undecidable. We won't prove that today, but just to think, how would you prove that this is undecidable? So we'll take a 5-minute break.